In this video, we're going to walk through backwards stepwise multiple regression model to predict electricity cost using 8 independent variables. To begin with, I've used Excel's slope and r-square functions to calculate the r-square and slope for a linear regression model using each of our independent variables. And in terms of looking at the r-squared, we can see that fabrication hours has the highest predictive value on an individual basis. After fabrication, next would be our machine hours, followed by machine hours at 37%. We've got roughly 21% by product C and 21% predicted by our heat treatment. So we'll pick up our product C and we'll pick up our heat treatment hours. After product C and heat treatment, we would find that our next best explanatory variable is product A. After product A, we would say our average outside air temperature. After average outside air temperature, we've got direct labor hours, followed finally by units of product B that we've produced. In running our stepwise multiple linear regression model, we're going to find that some of these variables at the top of our list aren't included in our final model, while some of the variables down here near the bottom of our list are included in our final model. The reason for that is these variables contain duplicate information. For instance, we're making products A, B, and C, and those are going to consume resources: machine hour time, heat treatment hour time, fabrication hour time, and hours of direct labor. So it's not surprising that our final model wouldn't include necessarily both sets of variables because of the duplication of information contained in those independent variables. That is, as our level of production of, say, product A increases, so does machine hours, heat treatment hours, and, say, fabrication hours. And conversely, we could say the same things with product B and C. And of course, products A, B, and C will consume different amounts of these resources, but there is some overlap in the information provided by these independent variables. Let's begin our backward stepwise method. In our backward stepwise method, our first regression model includes all of our independent variables. So in that case, it will include all 3 products: our machine hours, treatment, fabrication, direct labor hours, and our outside air temperature. Let's go ahead and run that regression model. We come up to data, data analysis, regression, and again we are trying to predict our electricity cost. We're going to include electricity up top, we're going to include a label, and we are going to try to predict it using all of our independent variables. And in terms of our output, let's put our output to begin with up here on near the top of our worksheet in cell L13. All right, our full model in terms of explanatory power, we have an R-square of 78%. So we're explaining roughly 78% of all of the variability in our electrical cost through the use of these 8 independent variables. But if we look closely at each one of the independent variables individually, we can see that some are providing useful or significant explanatory power and others less than useful or significant. In looking at heat treatment, which has the largest p-value or smallest t statistic, that indicates that it provides the least explanatory power of all of our variables in this multiple linear regression model. And again, this is somewhat surprising because it was 4th on our list as an independent variable with our simple linear regression model. But the idea here is that, again, some of our heat treatment hours is being explained by the production of products A, B, and C. So let's go ahead and run our regression again, leaving out heat treatment hours. So we'll come up to our data set. We will delete the column for heat treatment. We will run our regression again, data, data analysis, regression. Now in terms of our range of independent variables. Instead of going all the way over to column J, we are only going over to column I. And in terms of location of our output, let's not override our output, but let's put it down below, and we'll hit OK. In our new model, in terms of overall explanatory power, still a decent R-square, 77–78%. In terms of the least significant variable left in our model, again, we're going to look for the highest p-value, which appears to be on product B with a p-value of 32% and a t-stat of 1.02, so it's not significant at the 10% level. So let's go ahead and delete that variable and run our regression again. So product B, we'll delete that. Data analysis, regression. My data now goes all the way out to column H, outside temperature. In terms of where I'll put the data, let's put the data down here below our last regression output. With our reduced model now, we are still explaining roughly 76% of all the variability in electrical cost with our remaining six independent variables. In terms of the least significant one, that looks like that would be the average outside air temperature with a p-value of 0.28. So we'll delete our outside air temperature. And notice outside air temperature wasn't one that offered some explanatory power before, but let's go ahead and delete that. Run our regression again, data analysis, regression. Now we're coming over to column G, output range. With our most recent model reduced to 5 independent variables, we're explaining 74% of the entire total variation in electrical cost can be explained by these 5 independent variables. P-values at the 10% or worse level, we've got looks like machine hours at 14, but product C is the highest, so we'll go ahead and eliminate product C from our regression model. Delete data analysis, regression. We're coming over now to column H. In terms of our output, put it down here in cell H118. Okay, what do I've got? I shouldn't have increased that to letter H. I should have dropped it down to letter F. Now I think we're okay. In terms of our latest output, overall explanatory power of our model, 71% of our variation electrical cost is explained by the remaining 4 independent variables. And at a 10% level, all of them are significant. Now notice in the last model, machine hours was not significant at the 10% level, nor was product C. But when we took out product C, that left or increased the explanatory power of our hours in machining. And so our final model has these 4 independent variables. So our final regression model is our predicted electrical cost will equal to a fixed intercept of minus $1,895. Keep in mind that this doesn't make sense in the sense that if we produced nothing, we would have a negative cost. Again, this is our cost, fixed component of our cost within our relevant range. And within our relevant range, our slope coefficient for production of product A is $3.44 per unit. We're going to incur a cost of $7.78 for every hour we run our machines. We'll incur a cost of $8.81 for every hour of fabrication and $3.14 for every direct labor hour. And again, this is within our relevant range and assuming our production is balanced relatively in the same proportions as our input data. Let's go ahead and again, these coefficients are simply the numbers that we've picked up down here. Let's go ahead and predict our electrical cost at the following level of output. If in the coming period we plan to produce 250 units of product A and an unspecified number of product B and C, but our total production requirements would have required 360 machine hours, 500 hours of fabrication, and 700 direct labor hours, we would have expected an electrical cost of, we have to pick up our fixed component, we'll take our 250, multiply it by our slope coefficient for product A. We will take our 360, multiply it by our slope coefficient for machine hours, and the same thing with fabrication and direct labor hours. But we had an estimated total electrical cost at this level of production of, let's add those 5 numbers together, we would expect an electrical cost of $8,370. Again, one of the things we need to be careful of, and we're probably going to want to run a regression hour to make sure that to ensure that our fabrication hours and our machine hours and our direct labor hours are consistent with whatever levels of production we choose. That is, levels of production of product A, B, and C.